Okay, today we're talking about tests for proportions. So you're actually going to be able to do a one prop z-test for proportions. Okay, so this is the first half of the lesson. I think the next one is going to be two prop. Okay, so the conditions are pretty similar. Random, you look for the words random sample. If it's an experiment, I guess you look for random assignment, but less than 10%, same as normal. Nothing's changed about that. Large count is a little bit different. So let me talk conceptually about this as to why this is, and maybe this will start to make sense. So if you remember, we had a name for p hat. Does anyone remember the name? It is called the point estimator. In other words, when we were doing intervals, and so I'm specifically talking about intervals. When we did intervals, we used that to predict the value of p. Because quite honestly, we didn't know the value of p. The population parameter, we were just taking our best stab at it. That's the way an interval works. You say, that's my point estimate, that's my margin of error. I'm pretty confident the true proportion p is inside of my interval. But that's how it works, right? So we were trying to predict p. So when we did large counts, we did n p hat because guess what? We didn't know what p was. We had to use p hat. Do you remember when we did standard deviation with intervals? We had to use p hat. Technically, we called it standard error. We had to use p hat in standard deviation because we didn't know the actual p value. So we had to use p hat. So we call it standard error, standard deviation. When we check the large counts, we use p hat because it's all we had. Well, guess what? We have p now, right? So you can do n times p. So that little, in case you didn't know it, when it has that n p naught there, that means the null, right? You're talking about the proportion of the null. So whatever was given to us, whatever the p value is, the true proportion was given to us in the problem. And so you're going to use that, not p hat like we did before. We're not using that for, this is only for intervals, we use p hat. When you know p, you're going to use p. And again, saying the same thing there is basically saying that whenever you're doing this, you're using the p values, not the p hats when you do this. Okay, so this one, according to the US Census, the proportion of students in high school who have a part-time job is 25%. That sounds about right. Administrator at a local high school suspects that the proportion of students at her school would have a part-time job would be greater or less than the national figure, less than. So she would have to carry out a test at the alpha level. Alpha is called significance level. So a significance level where alpha is 0.05. And that's the typical one, very popular. The null is nothing's unusual going on. 25% of students have a job. But the alternative is, she thinks actually at her school maybe less than that. So the administrator selects a random sample of 200 students and finds that 39 of them have a part-time job. Check the conditions and see if performing a significant test are met. So the first one is random sample, and you can see it says the administrator selects a random sample. I would underline that, maybe draw an arrow to where you say random sample of 200 students. Less than 10%. So this one doesn't specifically say it in here, but I think you probably have to assume it's a local high school. You'd say 200 is less than 10% of all the students. You're assuming the school has more than 2,000 students, which I think is fair. Then the large counts condition. So in this case, you're going to do n times p, right? So 200 times 0.25. Which is, I think, 50, and 200 times 0.75, which I think is 150. And those are both greater or equal to 10. And so there you have it. Those are the conditions that are met. Again, the hard part is make sure you use p, not p hat there. You might be tempted to use p hat. Don't do that. So going back to the basketball player that shoots 80%, everybody thinks he's maybe exaggerating the truth a little bit. So the alternate is that he's shooting less than 80%. But the null is, hey, he's shooting exactly 80%. What value of p hat should we expect? Well, I'm not sure this is a question we're asked very often, but let's just answer it. So if the null is true, so in this case, if we make 25%, if you take 50 shots, so 50 times 0.25, oh, sorry, 50 times 0.8, right? Is 40. So you would expect maybe for him to make 80. Why does it say, I think the graphic is wrong there, right? So the graphic should not be that. Let me just fix that. So again, we would expect him to make about 40 shots, typically. That is what the question asked for. The shape, because the large counts condition is met, right, NP, so 50 times 0.8 is 40, and then the number of failures would be 10, so those are both bigger than or equal to 10, so because of that, we think it's going to be approximately normal. The center is the null. Nothing unusual is going on. So for the center of a test, we put the null in there, if that makes sense. So 0.8 goes to the center. And then you would calculate the standard deviation if you want to do norm CDF, which we will in a minute. That's what we're headed towards until you do square root of PQ over N. Again, those are not P hats. Those are P and Q. So you would be 0.8 times 0.2 over 50, all square rooted. Then you would draw your normal curve, right? Oh, I didn't change that one. I'll change that one in a minute. So draw your normal curve and shade appropriately. So 0.64 looks like it's pretty far down there, right? So you could do your norm curve. 0.64 is because he actually made 32 out of 50. So he made only 64%, which is less than 80. So write down this formula for Z. This is called P hat minus the null, divided by the square root or the standard deviation, which is square root of PQ over N. That's a pretty unusual result, right? Negative 2.83 standard deviations below the mean is more than 2 standard deviations gets pretty unusual. So this is going to be a very small chance, a very small p-value. If you do the p-value here, we can use technology to get that. So what you do on your calculator, if you remember doing norm CDF, so you would say menu 652, whoops, menu 652, and from there to negative 2.83, and then leave, because it's a z-value, you can leave the mean at 0 and 1. That's what they are for the z term. So it's 0.0023. Oh my goodness. So very small chance of this happening by chance. That's what they got as well. In the preceding example, an administrator at a local high school decided to perform a test at the alpha level of 0.05, where the true proportion of all students have a part-time job. The administrator selects a random sample of 200 students from the school and finds that 39 of them have a part-time job. We already confirmed the conditions. Explain why the sample result gives some evidence for the alternative hypothesis. So let's just kind of get our calculator out for a second. So 39 out of 200. So what is that? 39 divided by 200. I'll put a decimal point there. It gives me a decimal. So 19%, 19.5%. Well, that is less than 25%. So maybe people at the school do have less part-time jobs than normal. How do we calculate the standardized test statistic? So we go to, sorry, let me get to this. Okay. So on this one, So calculate the z. So z would equal p hat, which was, I think we just did that, 0.195. 195 minus p, which is 0.25, all over the square root of, again, we're going to use PQ, so this is actual p, so 0.25, not p hat, times 0.75, or 1 minus 0.25, all over, I think it was 200. So you would then type that in your calculator to get the z critical value. What conclusion would you make? Well, we have to see what that value is. So get that. We get negative 1.8, right? So if our z value is negative 1.8, so let's go back to this. So if you think about that, so we're going to do norm CDF, so menu, 652, negative infinity to negative 1.8, I believe. So there's a 3.5% chance of that happening is the p-value, given that the null is true. So what is our conclusion in that case? If we get negative 1.8, well, because the p-value of 3.5% is less than the alpha level of 5%, we reject the null. We have convincing evidence, because it's so low, that the true proportion of all students at a large high school have a part-time job is less than 0.25. So that's interesting. I wasn't sure that was going to be the conclusion, but that's what happened. We rejected because it was so unusual, the result that they got. These are the 4 steps that you have. You can write those down. So I just want to show you this. This is what you get in class. It's just a template kind of for one prop z test, which is what we're going to do in full here. So this is what you could use as your template. If you want to stop that and show that, you can. Okay. So first, I guess before we put it all together, just know what the conditions help you do. So the first condition is the random sample, right? And so the random sample condition, it really allows us to do that point estimator. So p hat minus the null, basically, is we are able to do that to find the difference between the two, because it's a simple random sample. Second one is the large counts. Large counts proves normality, and so we can't use z critical value unless we have a normal curve. We just can't. So that's crucial for that. And you probably remember from intervals that standard deviation is proved by the less than 10% condition. So we have to do that before we do standard deviation. This is just saying these are 3 different types of tests that happen. Sometimes we're trying to prove something is greater, the proportion is greater than they said, and that would be a one-sided test to the right. Sometimes we say less than, one-sided test to the left, and sometimes we say not equal to. That's actually a 2-sided test, technically. Okay, this is the example, again, that we have on our sheets. And you might be familiar with this. We talked about it before. Potato producer says the null is 8% of tomato or potatoes have blemishes. They get a truckload, they test 500 of the potatoes, and 47 of them have blemishes. Is there convincing evidence at the 10% alpha level that more than 8% in the shipment have blemishes? So you want to just kind of start going through and looking through stuff. So the first thing you need to do there is write, the null hypothesis. So in this case, I put a colon there, and then I put p equals 0.08. That was given to us. The alternate, because it says he thinks, I think he says it. Potatoes have blemishes. That more than 8%, I was trying to find that, more than 8%. So the alternate would be that p is greater than 0.08. So in the state, you also need to say, so the hypothesis significance level, so you want to say alpha I don't know how to draw alpha. Alpha, I'm not good at the Greek letters sometimes, but you get the idea. Yeah, I kind of looked at it. So alpha is, I think 10%, so that's unusual. Usually it's 0.1. You also wanted to find the parameters. So P is, and you say this in a word, the true proportion of potatoes that have blemishes in the delivery. Something like that on the truck. Okay. Part 2 is plan. So name the test. So this is a one prop Z test. That's the calculator name. That's the name I prefer. You could also call it a one sample Z test for proportions. That's the official name, but everybody will accept one prop Z test if you use that. We have to check the 3 conditions. You can see that it does say random sample from the truck. So random sample, check. I'd underline it in the word and draw an arrow. Okay, large count, so NP, so this would be 500 times P, which is 0.08. And we're hoping that number is greater than or equal to 10. And then 500 times Q, or 1 minus P, which is 0.92. We're hoping that number is greater than or equal to 10. And so use your calculator and prove that. I'll show you that in a minute. Less than 10%, so 500 is less than 10% of all potatoes in the truck. There's tons of potatoes in the truck. That's totally doable. P hat. So P hat is the 47 out of 500, whatever that decimal is. Z, they want you to show Z is going to be P hat. I guess you might want to do the 47 divided by 500. 0.094. So 0.094 times 1 minus that, so 0.06. What am I doing? I'm thinking of the second part. So 0.094, which is P hat, minus P, which is 0.08, divided by the square root of 0.08 times 0.92, all over 500. So you'll type that in your calculator and get your Z value. Let's see what they did. So they showed the hypotheses, the conditions. They got the same stuff we did there. They wrote it down the same, so you get 1.15. Now I know what that is without typing it in. So 1.15. That's our Z value. So when you draw this, you know, the nice thing about Z is, and it's a really bad drawing, by the way, it's just measured as standard deviation. So 1.15, somewhere over here is at 1.15, you're shading to the right of the 1.15. So that's where that value is right there in terms of Z. So then you get out your calculator. Menu 652. So it's 1.15. Whoops. To infinity. I'm just going to put a big number. And you can leave default because this is Z value. So you get 0.125 or 12.5%. So 12.5% is, you know, more than the alpha level of 10%. So because our p-value is 12.5%, is more than the alpha level of 10%, we fail to reject the null. We don't have convincing evidence that the true proportion of blemished potatoes in shipment is greater than 0.08. Be careful not to say the null is true or accept the null. Words like that will not quite fly. If you use your calculator, so let's go back to this example. Let's talk about how we can use our calculator. So let me go back to the problem, because you can actually kind of do the whole problem in your calculator. So if you go to menu, 6, 7, 1 prop Z test is number 5. Do y'all see that? P0, that means P naught there. It's like a subscript, but it doesn't look like it. So P naught is the null, 0.08. X is from the sample they took. They got 47 blemished potatoes out of 500. And then you choose the direction of the arrow. In this case, we think that it's going to be greater, or have more than 8%, so greater. And it should give you the z-value, very same v-value. In fact, this is more accurate than what we did by hand because I think we rounded a little bit. The p-value is 0.124 actually, or 12.4%, the p-hat. So if I'm doing this on my calculator, you have to be sure to write down the z value, the p-value, and the p-hat value. So if you use the calculator to do this instead of doing this by hand, you've got to write those three numbers down. You've got to get credit. So it's crucial. Okay, if you want to see another example, I think we have enough for today. Okay, so let's just, well, I'll just show you this. If you want to do this one on your own, you can look at the answers. So that's the question. Part A is that, part B is that, and part C is that. So just a good example. If you want more practice doing that, that's a good example of it. Okay, that's your screencast for today.